All right, now we're just going to review some trends in acidity and then talk about the last definition of acids, Lewis acids. So binary acids are the one that's just H and then another non-metal, so HF, HCl, HBr. The more polarized the bond, the more acidic the bond. And the stronger the bond, the weaker the acid. So your strength is going to increase as you go right. So you're going to increase your electronegativity and increase your strength of your acid. And then as you go down the table, you're also going to decrease your bond strength. They're getting farther apart. And so you're going to increase your acidity. They're going to ionize more easily. So you can see that hydrofluoric's a weak acid, but then HCl, HBr, HI are all strong acids. Here we can look at bond energy and see that trend. The bond energy decreases as we go down the table, and the type of acid goes from weak to strong. Oxyacids are kind of the opposite. The more electronegative the Y atom, the stronger the oxyacid. So for oxyacids, their acidity is going to decrease down a group, unlike the binaries, which increased. And the larger the oxidation number of the central atom, the stronger the oxyacid. So the acidity is going to increase to the right across a period, just like the binary acids did. And the more oxygens, the stronger the oxyacid. So HClO3 is a stronger acid than HClO2. So here we can look at electronegativity and acidity. You can see that as we get less electronegative, the Ka value goes down, so we become less acidic as we move down the table. Okay, so some practice. Order the following. Why don't you pause the video, review the trends, and then put these in order. So here, there should be a space in here. So we're comparing HPO4, HPO3. Well, HPO4 is going to be stronger than HPO3 because there are 4 oxygens rather than 3. And then we're comparing phosphorus, nitrogen, and arsenic, which go from nitrogen's at the top, on top of phosphorus, which is on top of arsenic. And so your acidity is going to decrease as you go down the table. So the least acidic is going to be H3ASO3. It's going to be less acidic. Then we said H3PO4 was less than, HP3PO3 was less than H3PO4 because of the number of oxygens. And then nitric is a strong acid. Okay, then by acidity least to most, we're going to get, let's compare these two first. When we've already lost a hydrogen, remember the Ka value decreases by quite a bit. So that's going to be our least acidic. Then we're comparing hydrochloric and hydrobromic. Hydrobromic, bromine is below chlorine, so that's going to be stronger. So we have HCl, HBr. Then by basicity, so the more, the stronger the acid, the weaker the conjugate base. So here we are comparing a bunch of top row, and we are oxyacids, and so the strongest oxyacid is going to be the one farthest to the right, so the nitrogen one. So the least basic is going to be the NO3 minus. And then next, as we're going across the top of the periodic table, nitrogen is number 7, carbon's number 6. And so we have 2 carbon options. Carbonate without the H is going to be more basic than bicarbonate with the H. So we're doing least to most, HCO3 minus, CO3 2 minus, and then our borate. There we go. Okay, let's briefly touch on Lewis acid-base theory. You will come across this more in organic chemistry. It focuses on transferring an electron pair rather than on hydrogens. So it does not require hydrogens. The electron donor is the Lewis base. It has extra electrons, so it's a nucleophile. It wants, it becomes more stable when it has another nucleus around it. The electron acceptor is the Lewis acid. It doesn't have enough electrons, so it's an electrophile. Phile means love, desire, that sort of thing. So an electrophile wants more electrons. Lewis acids are electrophiles. Lewis bases are nucleophiles. So a Lewis base is going to have extra electrons. It's willing to give away or share. A lot of Lewis acid-base chemistry is going to be forming new bonds. An anion is going to be a good Lewis base because, again, it has extra electrons. And generally, the more electronegative, the less willing it is to be a Lewis base. Lewis acids are electron deficient. There's a couple ways they can be that way. They could be attached to electronegative atoms, or they might not have an octet, and they need to have an empty orbital to accept that electron pair. So H plus is a Lewis acid as well. It has an empty orbital that can accept electrons. Boron and boron trifluoride has an empty 2p, incomplete octet. We mentioned those small highly charged metal cations act as acids. They also act as Lewis acids. And like I briefly mentioned, the Lewis acid-base reactions often form a covalent bond instead of just a transfer of something. It's called an adduct. And then Arrhenius and Bronsted-Lowry acid-base reactions also fall under Lewis acid theory. So when we're doing Lewis acid-base reactions, often you'll see arrows showing where the electrons are going. So here our Lewis base has extra electrons that it can donate to this hydrogen. The electrons in this bond all go to the chlorine, so we end up with this adduct where the H is now attached to the oxygen and we have the chlorine by itself. Here are the arrows always indicate where the electrons are going into that extra orbital that boron has to form this adduct.